And we are live. And welcome to Climate Chat. I'm your host, Dan Miller. And today we have a returning special guest, René van Westen. And by the way, say it correctly in Dutch.
René van Westen.
Okay. Close.
But it was perfectly already.
Okay. I'm sure you're quite used to having it said all different ways. René's a researcher in the Netherlands working on AMOC, and he's very prolific, as we're about to see, with a lot of different research papers that we're going to talk about. René was on about a year ago, and we talked about his paper called Physics-Based Early Warning Signal Shows That AMOC is on a Tipping Course. And by the way, I guess we should start off by saying the AMOC is the Atlantic Meridional Overturning Circulation, and it is the ocean conveyor belt, as often described, that brings heat from the tropics to northern Europe. And it's been slowing down, as we're going to discuss, over the last century. And if it collapses, we're going to talk about what that means. It would have very big, wide-ranging impacts, and we'll also talk about that today. So just get the definitions out. So first of all, welcome, and it's great to have you here. And to start off, rather than talking about your particular paper, I want to talk about a paper that seems to contradict what your paper says. And let me pull it up here. It's called Continued Atlantic Overturning Circulation Even Under Climate Extremes by Jonathan Baker and others. And it says, hey, you know, the wind-driven currents won't stop, and the AMOC won't go to zero, and all that kind of stuff. So to put it all in context, maybe you could just talk about that paper just a bit and why it sounds different than yours, and what does it mean for the AMOC to collapse?
Yes, I really like the question. And
I am not hearing you. Wait a second. Stacy, are you hearing René? Is it just my thing? Okay, keep going.
Okay,
then
I really so of course I've read the Baker study, which was published a few months ago, and I really like the study. And it's good to keep in mind that there were two different kind of differences between the two studies. So in our study we used freshwater flux forcing and no climate change, and in the Baker study they used climate change. And what is kind of interesting is that they all have an AMOC collapse in the Baker study on climate change, but their AMOC doesn't go all the way down to zero. So it remains in a very weak state. And this weak state, you could say that this is now also a collapsed state, but it is not like a fully collapsed state. But so with a fully collapsed state, you could argue that the AMOC strength goes all the way down to zero. So that is what we reported. And under climate change, there are so-called different kind of processes and feedbacks and wind-driven circulations that keep your AMOC at a very weak state. But if you then look at the level of the impacts which are then induced, like an AMOC of a zero strength and an AMOC of 1 sphere drop strength, they are actually the same thing. So we could still say it's a collapsed AMOC state, not a fully collapsed AMOC state. And if you then turn to literature, there's actually not a very proper AMOC definition or an AMOC collapse definition. So this is still, we need to address as scientists that we have like a proper AMOC collapse definition, but that is very hard to say at which level we can call it like a proper AMOC collapse or like a weakened state. So that is, of course, a issue we need to tackle.
Oh, okay. That's interesting. There's no good definitions. But when your papers that talk about, for example, the most recent paper, or one of the most recent papers about the impact on Europe's climate, what AMOC state are you speaking of then? How collapsed, I guess, is the question.
Yes, so we have, for example, three different kind of configurations, like a fully collapsed state that is like a 100% reduction in strength. So then we see some kind of impacts, but we also have impacts with 90% reduction or with 80% reduction, and they're not that different when you compare each other. So if you are below a certain threshold, which we don't know yet how much that is exactly, then the impacts are quite consistent among all the different kind of scenarios. So you could say in terms of the impacts, it doesn't matter that much if it is like weakened by 80% or 90%. So they are quite comparable to each other.
Well, that's interesting because in the Jonathan Baker paper, he says that the wind-driven, the Gulf Stream's wind-driven, and it's not going to collapse because the winds aren't going to stop. So there is no 100% collapse state, is there?
Yeah, but that's also a point we also mentioned, for example, in the media. The Gulf Stream will never vanish. Even if the AMOC fully collapses, it will never vanish. But the Gulf Stream is only a very teeny tiny part of the full circulation. Meaning that if you are only measuring the AMOC as the Gulf Stream, then you're like not completely measuring the same thing. So that's always
of course
separate. Yeah,
but it also means the AMOC, which includes the Gulf Stream, doesn't go to zero ever, right? I mean, that's not one of the possible states, is it?
Well,
zero.
Maybe it can, but that is some kind of limitations we now use with the models and the different kind of configurations. So in our setup with a pre-industrial constant climate, the AMOC can actually go to zero. But of course, the question is if you have a different kind of forcing, a more realistic one, such as an increase in CO2, maybe you end up with a slightly different configuration in which the AMOC is non-zero. And that is also the key message that the Jonathan Baker paper shows, is that the AMOC is weakening under climate change. So that is consistent with the IPCC report, so that is not something new. Right. But of course, the end state, whether that is like zero or maybe 2 swirl-drops or 3 swirl-drops, well, that is of course still debatable, and we don't know at which level the AMOC will end under extreme climate change.
So this is actually a more interesting subject. I think it was Johan Rockström in Real Climate, or somebody else was writing about this paper, saying, first of all, no one ever said the wind-driven are going to shut down, of course, as you just said too. Well, and also that he showed a picture where it was a reduced state. I don't know how much reduced, and this new paper used exactly the same models. It was exactly the same figure. And in the first one, since it was people talking about AMOC collapse, it said collapsed AMOC, and this exactly the same point in the new paper said no collapse. It was exactly the same, but it didn't go to zero. So,
Yes, but that's more of a technicality than rather, again,
semantics
this
or something.
It's I would say it's of course the definition what we want to use also as scientists, and to have a proper definition. But I think that or at least most scientists would agree that this is a collapsed AMOC state, but not like a zero collapsed AMOC state. And maybe that's also part of our paper, which was published last year in 2024, where we really had like a proper full collapse all the way to zero. So perhaps that also, influences their kind of interpretation or framing, etc.
So when we talk today about your other papers, and they're all to do with AMOC collapse, what kind of AMOC collapse are you speaking of? A realistic one that we could be experiencing the end of this century, or some quite future, much lower state?
So in the end, it is very important to keep in mind that timescales of an AMOC collapse and also of an AMOC tipping event. So the climate projections indicates that the AMOC is expected to weaken under future climate change. So that is very robust among all different kind of climate models, and also for different kind of climate scenarios. So that is a given, and that is fairly well demonstrated even also with other previous climate models. And that is, we can call, of course, AMOC weakening. But then the question is, when do we reach this tipping point? So is the weakening part of the collapse? Can we distinguish them? And that is, of course, very hard to say. But the complete AMOC tipping event takes at least 100 years.
Right.
So that means that by the end of the century, we are probably in a weakened state, but we cannot say whether that's already like a collapse state, because we are still in the transient, going to a weaker state, or maybe the AMOC already has stabilized and then eventually we will recover. That is something we don't know, because the timescales are relatively short compared to the full AMOC tipping timescale.
But there are these tremendous impacts that we'll talk about a little bit later. I guess the worst of them will come if it goes down to a very, very weakened state. But we could see very, very serious impacts even under halfway there or something like that, later in this century time frame, right? Is that right? Or?
Yeah, so even a substantially weaker AMOC, already by 30 or 40 or 50%, you can already see these kind of effects. And the stronger the weakening, the more impacts the AMOC will induce on different kind of parts of the world. So a weaker AMOC causes, of course, a lot of bad climate impacts for society, but also for ecosystems, etc.
Okay. So why don't we jump into, let's see, I'm going to try this one here and make you the bigger here. And I'm going to try to add just a picture of your paper here, if this works. Screen share. And let's see, does this work? And move it here. So this has substantial risk. I'll do this so that people can see it. Substantial risk of 21st century AMOC tipping, even under moderate climate change. And this is this a preprint or is this?
This is a preprint.
Okay, so this is a paper has not been officially accepted, but it's going through the peer-reviewed process now. Is that right?
Yeah. So okay. This original paper was initially rejected for publication. So we've been reworking the paper. So this is already outdated, but we're trying now a different kind of format of the paper. But part of the analysis that is still now much better motivated, and therefore we of course need to be very careful when we speak about preprints, because that is also with science, things change quite a lot. Upon initial submission and the final product, which is finally published.
So okay, so and this one follows the paper. Oh, by the way, I should say that our interview with you from last year is a link to it is in the YouTube description. Definitely check out that. I listened to the interview again earlier this week. It's a great interview. Everyone will learn a lot about AMOC, and especially a kind of mind-blowing discussion about the impacts, which we'll also cover a little bit today. But that paper, again, physics-based early warning signal shows AMOC is on a tipping course. And now this paper, substantial risk of 21st century AMOC tipping, even under moderate climate change, so it's preprint. So what's new in this paper compared to the old paper?
Yeah, actually this motivation of this paper comes from the discussion we had with all the media, also with you, Dan, is that, so in our study from last year, we only had like a pure AMOC experiment. So there was no climate change. We are only adding fresh water into the North Atlantic Ocean and see whether the AMOC can collapse. And the answer to that was yes, it can collapse under this freshwater flux forcing value. But there was also critique that we didn't consider any climate change and that our forcing was not real. And we completely agree. That was also part of our discussion. So in this new paper, what we actually now we're incorporating is that the effects of climate change are considered, and to see whether also the AMOC can collapse under climate change. And then we have two different kind of scenarios, which is an intermediate climate change scenario, and with intermediate, which is still quite severe for the global society, but that is about +2 degrees warming by 2100, and we have a high-end scenario, which is about 4 degrees warming by 2100. And we were interested whether these effects of climate change, which generally results in warming all over the globe, can compete against this AMOC-induced cooling, especially over northwestern Europe. So we were pursuing that goal and to see whether we can first have an AMOC collapse under climate change and what these effects are still. Whether is the cooling the dominant signal or is the heating the dominant signal. And that really depends on the scenario. And we also have different kind of papers following from that, which looked in much more detail on these kind of different impacts particularly for Northwestern Europe.
Okay. And so, and in the abstract, it says that under the moderate climate scenario, I think there's a 50% chance of collapses century, right? No, greater than 50. And then it says if it's the high end, it's a 90% chance of hitting the tipping point this century. So my question is, Jim Hansen has recent research showing that the equilibrium climate sensitivity is 4.5 degrees for a doubling of CO2 versus the IPCC's 3.
Mm-hmm.
So my question is if he's right, does that mean even your moderate scheme is still up in 90% time? Like if ECS is much higher than the current discussion about it is, what does that say about AMOC risk?
Yeah, so this is also the problem with this preprint is that we had to go back to the drawing boards, and therefore a lot of conclusions has changed, and also the interpretation on that. So we were also trying to come up with a certain threshold when the AMOC is likely to tip, because that in the end that is also very helpful to communicate with the public, but also with policymakers. If there is a certain temperature threshold, you know that the AMOC is likely to tip. And for example, if you take the study from Armstrong-McKay back in 2022, they assigned that the AMOC is likely to tip from 4-degree warming and beyond. And without using those numbers, because those numbers are not valid anymore from the study, we know that for additional warming, the AMOC is more likely to tip. And that is also a part which is already shown in the Armstrong-McKay study as well. This is debated. So that means if indeed the climate sensitivity is way higher than in the Hansen study, the AMOC is also way more likely to tip. But of course, to use all the numbers from that preprint, that is not relevant anymore. So therefore, I'm a little bit hesitant about that.
Yeah, because one of the numbers is 3C would be the threshold. But you're saying it's a preprint. You're going back to look at that so that 3 degrees Celsius global average temperature is not the threshold anymore, or may change?
No, that may change. But imagine if it is 3 degrees warming, if of course the climate sensitivity is much higher, then it is of course much more likely to tip. But that's we need to see what the climate sensitivity is, and also what the threshold of the AMOC tipping event actually is. Yeah, we don't know for sure.
Okay. Okay. So would you say that the new paper is relatively consistent with the paper we discussed last year? I mean, it adds this whole new layer to it.
So it adds the whole new layer of climate change. So in that sense, it is more realistic, but it also has a few drawbacks because we are still adding an unrealistic amount of Greenland melts to the Atlantic Ocean to get the AMOC in a more sensitive regime. Because in most climate models, the AMOC is overly stable. That means that it is very hard to get it from one state to the other state, even under climate change. And we know for sure that the most climate models are in this incorrect regime. They have an overly stable AMOC. So we need to tweak the AMOC a little bit, so adding more Greenland water in the background to get a more sensitive AMOC. But that is, of course, very unrealistic, because that's not, of course, that is happening in the real case, but not at these kind of levels. So there are still, even with this new paper and what we want to pursue in that paper, there are still some drawbacks and some criticism that this is not realistic. And we hope, of course, that the new generation of climate models have fixed this kind of bias, and that they have like a correct AMOC, which is responding well to the imposed climate change scenario and the forcing.
Yeah, and Hansen says that the older models are way too insensitive to an AMOC collapse. And when you correct I think he just said it was the ocean mixing aspect of it. And when you correct that, and plus you assume much more melt from Greenland than they were assuming, because the world is warming faster than that was assumed, that you hit AMOC, a tipping point in around mid-century. And he said this quite a long time ago. And then many other people have come along to say the same thing. So your next paper, collapse of the Atlantic Meridional Overturning Circulation in a Strongly Eddying Ocean-Only Model. Let's see if I can, I don't know if I can, here we go. And let's see, let's go back to here. And
yes,
there we go. Okay, so tell us, okay, so we just learned how you took your original paper from last year, you added a climate model on top of it and learned a lot, and you're still working on that one. This one, by the way, is this one is published. This one here. Okay. And so tell us what's new in this paper and how does it add to what we know about AMOC?
So what was also a next question also from our previous study is whether can the AMOC also collapse when you have a very high resolution ocean model. So in this model, we have a very high horizontal ocean resolution, meaning that we resolve these so-called mesoscale features in the ocean. These are the big swirls. They look very beautiful in animations.
Right.
And in our previous model, we didn't, of course, they are parameterized, but they are not explicitly resolved. And there was also criticism from my colleagues. They say like, okay, you've shown this in an impressive way, but we are still missing these ocean eddies, these big swirls. And in this paper, we actually looked at the model which resolves these big swirls in the Atlantic Ocean and elsewhere in the global ocean. And we also showed that the AMOC can tip when you resolve those mesoscale features, because they can have like a composition effect, so they can stabilize the AMOC, but in the end, the AMOC can still collapse even if you resolve these big swirls in the Atlantic Ocean. And it actually follows the same kind of behavior compared to the more simple model, like all the different kind of early warning signals, the destabilizing mechanism, they still hold even in a higher detailed climate model. So that is, of course, a very big, important message that with a more realistic ocean, we can still have an AMOC tipping event.
But in this higher resolution model, when you got into that resolution, did the probability of AMOC collapse increase, decrease, or stay the same?
It remains the same, or we don't see any more worrying effects. But also, this kind of ocean model we used, it still has biases, so we still need to correct for these biases to get a more sensitive AMOC again, so that we are still having this kind of same issue. But the most important point is that the destabilizing mechanism, which causes this AMOC tipping event, that is still robust among the different kind of horizontal resolutions, which is very, that's of course worrying, but it is also meaningful for us. That means that resolution is not such a strong effect of stabilizing your AMOC or whatsoever. So yeah, it remains resilient, the conclusions.
So people were concerned that when you take a simple model of the ocean, it shows collapse, but maybe they thought, well, maybe when you get a more realistic version of an ocean model, it would no longer. But that wasn't the case.
No.
And so we still should be worried. We still should be worried about the AMOC collapse.
Yes,
right?
but what is very interesting, and that also connects with your first question, Dan, that our AMOC in that high resolution, more realistic model, it doesn't go all the way down to zero. It remains at a very weak state.
Right.
So. And we still call this a collapse state because it shares all the characteristics, but there is still a very weak residual AMOC remaining in the Atlantic Ocean. So it is a non-zero state. So it's not a fully collapsed state, but we argue that it is a collapsed state, but it is different compared to the more simple version.
So for our audience, let's. What is, I know it's considered a flow, what, in Sverdrups or something? I don't know how to pronounce it.
Sverdrups, yes.
So a non-collapsed AMOC before it started slowing down, roughly how many Sverdrups of flow was there?
So that is 17 Sverdrups, and
17.
That means 17, and that means 17 million cubic meter per second.
And that's a lot of water.
That's a lot of water. I think it's about, I'm not sure, I think it's about 4,000 Olympic swimming pools per second.
Okay. And then Stacy's asking, how is it spelled? I think it's SVEERDRUP. Is that right?
Yeah.
SVER. Yeah. There you go. Perfect. So, okay, 17. Now, what is it now? Let's say, is that what it is now, or is it?
It's still around the same level.
So I thought it's like 15-20% down from its.
Yeah, so that is still the variability of our measurements we see. So there's this measurement array along 26 North, so that is near the Strait of Florida. And the variability is so large that it is very hard to say or to detect any long-term trends
Although your next paper is going to
Yes.
be talking about that. We'll get to that in a second.
Yes.
But let's get to the final. But when we're in a collapsed state, not the fully collapsed, but the collapsed state, what is the flow rate then, do you think, in order of magnitude?
Yeah, so that's of course now very interesting, because in the more realistic ocean model, it is about 5. So that is
okay.
75%.
So like from 17
reduction.
to 5, that sounds
that's
pretty serious.
Substantial. Yeah.
Wow. Okay. So it's all like coming together here, because your next paper, let's see if that one worked. Deep learning-based reconstructions of the Atlantic Meridional Overturning Circulation, AMOC, confirm 21st century decline. So please tell us what's going on in this paper and what you learned.
Yeah, so this work so it was led by Simon Michel. So I'm a co-author on this paper.
Right.
And what important with this paper is that it addresses a very important point of debate among the AMOC community. Has the AMOC weakened over the past century? Yes or no? That's an outstanding question. And if you take different kind of metrics, different kind of time series or reconstructions, because we didn't have any measurements of the AMOC since 1900, we need to reconstruct the AMOC with available records which are available.
Like proxies, right?
Exactly. And what is a very important and very popular proxy, that is the sea surface temperature, because that one is pretty well measured throughout history, or throughout since 1900, because a lot of ship measurements were done. So people log this, so we can actually have a quite realistic and reliable data product. But of course, it has some drawbacks, because it has not a complete coverage and only over the North Atlantic Ocean. And there was this paper from Caesar and colleagues in 2018. They proposed this metric using sea surface temperatures, and they showed that the AMOC has weakened by about 15% since 1950. But there was a ongoing and very extensive scientific debate whether this reconstruction can be used, because they are using the sea surface temperatures in the North Atlantic Ocean region, but this can also be influenced by winds, by atmospheric circulation, by aerosols. So there are a lot of processes that can influence this proxy, this reconstruction. So there was a healthy scientific debate whether this was now the correct interpretation, yes or no.
Right.
And what we now have done, or Simon, so the lead author, has done, so he looked at using machine learning techniques and using much more data to put into this black box. So in this machine learning algorithm, to get a more robust trend out of that. And what it actually shows is that, yes, using all available data, so not only this small part in the North Atlantic Ocean, but looking at all the available data in the Atlantic Ocean, we see a very persistent and consistent decline of the AMOC in the 21st century.
Now, what are some of these other, like, is it just more temperature data from other parts, or does it include wind data? And what are the other things you're throwing in the black box?
Yeah, so it is mainly using temperature data, but also at the lower latitudes. So it is much more consistent, and also not only only focused on a very small region around the Greenland, but it is using like the whole available longitude. So that is from the east to west coast in the Atlantic Ocean. So it is assimilating much more data, and also shows that we get a much better temporal reconstruction of the AMOC strength time series. And it is still, of course, a reconstruction, but it is trained with available models, available data. So this is like an updated version of the Caesar index, which was proposed back in 2008. So, and that is actually very nice that it is still underlying from the previous study from Caesar and colleagues, which was already a very well cited and very well received paper. So it's nice that there is now much more evidence that the AMOC has declined over the 21st century and before that.
So I guess an important question is what does it show? How much decline does it show over since the beginning of the measurement or something?
Yeah, I thought it was about 15%, but
so that's what it was. That's what it was. So it's basically confirming what was thought before.
Yes.
That was, I think, the number that was. Now, Peter Diblicson did a well-known paper where we had him on as well, where he did a statistical analysis showing that the AMOC would decline. But I believe, and we're trying to remember this if I get it right, that he used this measurement as the statistical in his model. So I guess he could update it with your data, or maybe your data is saying the same thing. So maybe that means his analysis is still valid.
Yes. So the analysis proposed by Peter Diblicson uses this smaller region, and now, of course, you can retry with this more updated version to see whether the conclusions still hold. And we also addressed this this in our 2024 study. Is we used Peter's work to also see whether it holds in our climate model simulation. And there we actually show that this smaller region is very prone to false positive alarms. So then you see like, hey, everything goes up. This could be the case that the AMOC is going to collapse within an X amount of years, but actually it was a false alarm. So it also sometimes it works very well, but other times it raises a lot of false alarms. So, and this is also being discussed within the AMOC community, as there was the study from Benyami and colleagues. They also show that it can be very sensitive to the methodological choices and the kind of time series you're analyzing. So, yeah, there is a healthy debate among the AMOC scientific community.
Okay, well, that's I guess good. So, what does this paper say about future decline? Does it make any? Is it just simply measuring, or is it looking to the future as well?
Yeah, so it uses a combination of both historical observations, try to reconstruct the AMOC, but it also shows that the AMOC is projected to weakening, and that is also underlying this in the paper, is that it gives more support that we are expecting that the AMOC will start to weaken during the 21st century.
And then I guess one of the important questions, you said, is it weakened about 15%, but there's some threshold where it weakens so much, and I believe the AMOC is sort of self-reinforcing, that brings its own salt to the party, and if you keep weakening it, then eventually it will start weakening on its own, and then that's when you're at the tipping point. Yes. Is there any agreement on what the threshold is? So 15% already, is it 30%, or is there any feel for that?
That's a really good question, Dan, and that is also what we want to try to answer that question in this preprint. The first preprint we discussed. Mm-hmm. So we're trying to answer that. Can we give a more or a better distance to the tipping point? In the end, we want to communicate that with policymakers to give a real year, but that's of course very hard to do so in the first place. So that is what we're currently working on, trying to get this, but that is still work in progress.
So what's the range? Because it's more than 15% and it's less than 100%.
We don't know.
Oh, yet. Okay. It really is that open. Okay.
Yeah.
Wow. But if it's that open, how do you come up with your papers that say AMOC is this likely to tip this century? I mean, you have to have some idea what tipping means in order to come up with a time frame.
Yep. So the problem is with most climate models is that they only run the simulations till 2100 because it's computationally very expensive to run.
Okay.
And therefore we want to figure out, so can we already find like an indicator? If this is like flagged, then we know that the AMOC is very likely to continue to collapse when you are going beyond 2100. That's something what we would like to know. And we're now trying to develop such an indicator that we know okay, this may happen in a climate model. And if you then look at a whole ensemble of climate models, then you can maybe say something about the probability of that. But again, with a drawback that climate models are biased, but it can give us some impression that we know that this is the future trajectory of the AMOC beyond 2100.
Okay. Okay, well, let's move on. Let's see if I can get this other paper. Here we go. Let's try this. Changing European hydroclimate under a collapsed AMOC in the community Earth system model. So tell us what this paper is all about. And and this is also Is this
a preprint?
This is a preprint. You're the lead author. Okay.
Yeah.
So tell us about this paper.
Yeah, so this is also a preprint, and actually this is work is part of the KNMI. So I've been working there for half a year, and now back again at Utrecht University, and we're actually analyzing three main topics. So one, what are the temperature impacts? So that paper, I can say that it will be accepted and be published in the nearby future. And the second question is also, and that's this paper about what will happen with the precipitation changes when the AMOC collapses, because there were a lot of responses. So for example, if you take Northwestern Europe, if the AMOC fully collapses in our climate model from 2024, we saw a 20% reduction in annual rainfall.
20%, okay. So which is a lot.
That is substantially, yeah.
That's a lot when you're trying to grow food and things like that.
Yeah, and you can imagine that if you are growing foods with a lot of colder temperatures and on top of that also less precipitation, it will be very hard for farmers to still maintain their lands. So that is, of course, also a very important topic to address. And this was in our 2024 study, we only looked at annual averages. Otherwise, the paper is getting way too extensive. And with this paper, we're really trying to address what is going to happen with the precipitation changes, specifically done for Northwestern Europe, so more of a case study, and to see how it will respond, what are the drivers, and also what is kind of important to address, we also consider the effects of climate change. So we have like a AMOC collapsed without any climate change, but also if we are now also adding climate change on top of that, will it get worse? Maybe it will get better. So
maybe it could counter climate impacts to some degree, right?
Yeah,
possibly. But you're under AMOC collapse. You're stopping all this warm water flowing into the northern hemisphere. We had Matthew England on Climate Chat before we were on YouTube, when we were just on Clubhouse, and he had a paper that showed there was like 1 millimeter less of rainfall, 1 millimeter per day, less rainfall across the entire northern hemisphere, sort of on average. It varied. And that's a foot a year less rainfall on average, which has to have a huge impact on agriculture across, and not just Northern Europe. And there was a study about the UK, the one I could find that was like specifically like what you did for Europe, it did for the UK, and it said UK loses 2/3 of its arable land under an AMOC collapse. So also you mentioned that this is like 20% less. That's like the average rainfall. But when you change the averages a little bit, the extremes change a lot. So that could mean like much more droughts than previously.
Yeah, and what we also show in the paper that, in the preprint, I have to say it correctly, in the preprint, is that on an annual basis, there is a reduction, but the drying during the dry season, so that is usually what we define from April till September, so that is also during the growing season, when you have, of course, a lot of harvest going on, etc. There you can see that the drying becomes even worse. So that the 20% is an annual average, but there are seasonal differences. And that is, of course, very, very worrying, and also a very important message again for farmers is that this is a scenario. If the AMOC tips, of course, we don't know what the kind of probability or the risk of this is. These are the related impacts. So making it much more focused only on one climate variable, rather than looking at all the different kind of climate variables, because you can imagine that tons of stuff is going on if the AMOC starts to tip. And therefore, it's very important to address these kind of relevant questions, which were posed by you, Dan, but also other members of the public. They are interested what's going on with precipitation. So therefore, this is the motivation, like of all the media outreach with you, and also of all the people in the chat. So that is really inspiring, having this kind of connection with the public.
Well, speaking of that, when you were on last time, we talked about the overall impacts of an AMOC collapse, not just rainfall in Europe. And it was kind of mind-blowing, actually, to hear it again when I listened last week. Let's just go over a little bit, just for one little fun tidbit. What happens to the temperature in Bergen, Norway, if there's a I guess that's a full AMOC collapse, as you're talking about it at that point?
Yeah. So that was from our 2024 study. So we didn't consider any climate change there in that paper, so that's good to keep in mind. But what we then saw for Bergen, in such a scenario that the AMOC starts to tip, the temperatures over Bergen in Norway, that they can decrease, specifically for the month February, by 35 degrees over a century.
Celsius, by the way. So
Celsius,
35
yes.
That's just incredible. And keep in mind that's relative to the Earth warming on average 1.5 degrees Celsius so far. And all the impacts we just saw, we're seeing now, just from that average. It's a little bit more in the Arctic, of course. But even in the Arctic, it's 3-4 degrees warming. You're talking about a drop of on average, or is it wintertime, or is it something like that?
It's specifically for wintertime, so February.
So the wintertime drop going 35 degrees Celsius. And so basically what happens to Northern Europe and Scandinavia is it becomes like where it's located. It becomes Alaska and Northern Canada, because that's where it's located. And the only reason it's a nice place to live is because of the AMOC. Is that
exactly
right?
Yeah, so our climate actually in Europe is quite kind of skewed. So we have a much warmer climate compared to other latitudes, such as North America. And then our climate becomes more of a North American climate at the same latitude. So therefore, we're also here in the Netherlands, we would expect more of the southern Canadian climate. So actually, our climate becomes more equilibrated among other latitudes.
Yeah, no, I'm just wondering, I'm hearing a little funny choppy sound, but it might be me, since I seem to be having the trouble. I was asking like Stacy or Leon whether your audio is okay. But well, let's just keep going there. I think it's okay. I can still understand you. So let's talk about some of the other good. Okay, it's just my problem. Good. Let's talk about the other impacts, like sea level rise, for example, over on the U.S. East Coast, on top of whatever other sea level rise there is. What kind of impacts happen there?
So the AMOC is, of course, influencing temperatures, precipitation, but it also modulates the local sea level, especially in the Atlantic Ocean. And also in our study, we looked at the dynamical sea level response in the Atlantic Ocean. And then you can see that some locations showed an increase of 1 meter of additional sea level rise on top of the current projections. And again, this is quite a lot. We didn't look into much detail along all the coastal regions, but we're also now, that is like on 3 papers that I'm working, one on temperature, one on precipitation, and the third one and the last one is on sea level. So how does this will look like under a AMOC collapse scenario? And also we're considering coastal locations along the North American coastline, but also for Northwestern Europe, to see what the impacts are. But this work is still in progress, so therefore it is not very useful to share anything. So it is not ready for a preprint yet.
Well, I can ask you what you think of Jim Hansen's suggestion that with an AMOC collapse, obviously all the things happen to Europe, but also what happens is that warm water that was going to Europe stays in the Southern Ocean, accelerates melting from Antarctica, which is not a good thing, and leads to several meters, in his words, of sea level rise at the end. I won't say like by the end of the century, but at the end of the century, maybe a little bit more, but still mind-blowing, several meters, 10 feet plus of sea level rise, the bottom third of Florida no longer on the map. I mean, the people don't get a feel for what this all means. And is that a realistic, is that a possible scenario?
So the AMOC effectively transports heat from the southern hemisphere to the northern hemisphere. And when the AMOC shuts down, all this heat will stay in the southern hemisphere. It will not reach the northern hemisphere. So therefore, you see this cooling in the northern hemisphere, and while there's warming in the southern hemisphere. And you can definitely imagine that a warmer southern hemisphere, a warmer Antarctica, will enhance melt rates over the Antarctic continent. So that's, of course, a very worrying signal. But to actually see what the impacts of the AMOC are in specific on the Antarctic ice sheet, you actually don't need to look at the surface. Of course, that's a very important contribution, but the actual melting mainly takes place due to the ocean, because the continent is so cold that even a increase of about 1 degree warming will not get it way above the freezing point. Of course, some glaciers will definitely melt, so that's of course very worrying. But you need to look at the subsurface ocean, whether that is increasing or decreasing the temperatures, because that controls the amount of basal melt. It's so called for Antarctica. But we didn't look at that yet, and I'm very curious to see whether that's whether the AMOC can stabilize or destabilize it. But looking only at the surface temperatures, it is a very worrying signal that the temperatures are increasing over Antarctica, and that will definitely enhance the melting of the Antarctic ice sheet.
But an AMOC collapse will certainly lead to warmer ocean temperatures around Antarctica, right? I mean, for sure. And that's what you say. That's where it's going to melt.
But the most important things happen at subsurface, so that is slightly below the surface. So maybe the surface warms, but the subsurface may cool, or it also simply warms. So that is, of course, a very also important question to address, to having these connections with all the different other tipping elements of the climate system.
Okay, so let's go back to Europe for a moment. And so one thing that happens with the AMOC is that the Northern Europe, Scandinavia, UK get really cold. That's the day after tomorrow scenario, but totally fake movie. So don't rely on that movie. But the general concept that it gets cold up in some places is true. And by the way, including Greenland, right? It could stop the melt, and it could do some positive things in the Arctic, but you don't want to trade that off for the Antarctic, because the Antarctic's a lot bigger. But in any case, in Europe itself, and maybe in your study on rain, is there a big difference between Northern and Southern Europe? Because I've heard that AMOC collapse could offset global warming in Southern or Mid and Southern Europe, and of course make it much colder in Northern Europe. But what did you learn?
An AMOC collapse has the most impacts for Northwestern Europe, so the regions closer to the North Sea. I'm not sure that people are familiar where the North Sea is located, but Northwestern Europe, that shows the strongest cooling. But what's good to keep in mind is that a AMOC collapse doesn't stop global warming. It will still continue to increase the global warming signal. It can only offset the regional warming, so not the global warming. So therefore, it is not like, oh, we're now saved. No, it is like a very, very bad message that if the AMOC starts to tip, we are looking at a rapid and drastic climate shifts, not globally, but also very regionally. So that's also to keep in mind that a lot of people say like, hey, global warming is now fixed. No, that's not the whole picture. That's only looking at temperature, but then on top of that, we have precipitation changes, but also additional sea level rise. So looking at only one climate variable, that doesn't tell you the whole story.
Okay. And Leon, if you're there, turn on your camera. If not, we'll go to Stacy first. I don't see Leon ready there. So Stacy, welcome. And let me get Renee over to the big spot there. Okay. And first I'll say welcome. And what's your question for Renee?
Well, I heard you talk about the AMOC.
Hearing anything, but if you can hear, keep going.
Yeah. I heard you talk about the AMOC community, and I just wondered how many people is that, and how long have you been a community?
Sorry,
I was wondering, you talked about the AMOC community, and I wondered how many people is that, and how long has it been a community? Because it seems like there might not have been much going on until, fairly recently.
No, there has been a lot of contributions, and the people have been very active with that. So the AMOC is very well studied, but of course it got picked up by the media, especially in the past couple of years. But if you look at all the different kind of papers who study AMOC, theoretical framework, there has been tons and tons of contributions. So it has been around for decades.
Oh, okay. Yeah, I'm not skeptical. I'm just
No, 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 no,
curious,
no, no,
like
no,
how,
no,
like
no.
who gets into this, you know? And then you also mentioned that it's computationally very expensive to include some of these things in the models. And I'm just, I just keep going back to how much does it cost if all this stuff stops? So, like, do we need to pass the hat? Like, how much money are we talking? You know?
I'm not too sure about the money, or I know it's a lot, but you need to reserve a lot of computational time on supercomputers, and of course that costs you like an X amount of euros or dollars per computational unit. So I don't know the conversion for that, but we use, for example, 3 million CPU hours to get everything up and running. So that's quite a kind of a lot of computational
Yeah.
resources that we need to request, and of course also get funded. The Professor Henk Dijkstra, so he knows all the details about this, but it's these are like a lot of computational resources, and we're very happy that we can access that and use that, because otherwise we cannot advance our studies as well.
Do you work? I mean, NVIDIA has a climate department now. Like, does anybody? But I don't know. I should check on what they actually do, because it seems like that would be right up their alley. Like, trying to help, with the computation, right? I mean, yeah.
Yeah.
Okay. All right. I'll get on the phone with Jensen and we'll get this sorted out. Yeah. There have been a lot of questions on YouTube. Is Leon still?
So Leon, let's finish with Leon, because he has some more sort of regular questions, but then we'll get back to you, Stacey, with the
That
YouTube.
sounds good.
So let's get rid of this and hold on one second. And Leon, welcome.
Hi. Yeah, we were teasing Dan a bit that we were going to speak Dutch here, but we won't. Let me please share my screen, because that always helps me to answer the questions. Can you put it up, Dan?
Let's see. Oh, I can.
Did I do it?
There we go.
Yeah, I thought I'll just get the units on there to for people to understand. You already covered it a bit, but so 17 sphere drops, that's 17 million cubic meters per second, and that's about 1 petawatt of heat, which has 15 zeros, which is a million times a billion joules per second, which is 32 zetajoules per year. And as my friend and colleague James Hansen, when I talked to him when he was here a while back, translated it's equal to 4 watts per square meter over the entire northern hemisphere, and that's also really an enormous amount of energy. So yeah, I think it helps. Like, I don't know if anyone can grasp these numbers. I sure can't, but I think it's
me neither.
Several million Hiroshima atomic bombs going off every day. Several million. It's equivalent to several million Hiroshima atomic bombs going off every day.
Yeah, so several million Hiroshima bombs worth of heat transported through the Atlantic Ocean northward. Indeed, that's nobody can grasp that, I think, but that's what's happening. And I'll just, so I think this, I would like to hear your thoughts on this in a second, but this is the ERA 5 data. It's a reanalysis data showing the transport through the top 1,000 meters of the North Atlantic. This is sphere drops. So you see there's a very strong decline in this reanalysis data. So these are models, these are not observations, but as René already explained, it's quite hard to get these observations. And this is the absolute numbers, these were the anomalies, and here's the same in petawatts. So this is sphere drops. This is, as René mentioned, this is about 17 sphere drops worth of heat transport northward. These are latitudes, these are years. And then here's in petawatts, the same graphs. Yeah, so maybe you could start with talking about like how reliable are these reanalysis data, or how reliable are the different data sets we have?
Yeah, so this is reanalysis data set. I often also use this data set because it goes all the way back to 1958. And then you can also see whether the climate is, or like, first I have to say, like, historical observations are assimilated in this product. And usually the data is quite close to these observations, but sometimes you're missing data and then the model fills in these gaps. So it is very useful to see like the long-term trends. But if you really want to look at a temporal variability, like on a sub-seasonal scale, they are not always that realistic. But what it actually shows is that this very decreasing trend, which also showed up in other products, and also the second paper we discussed by the lead author Simon Michel. Oh, there's an echo again. Yeah. So that is also showing a weakening trend of the AMOC during the 21st century.
Then can you switch off your mic?
Okay. Sorry, what's going on here? But
sorry, what were you saying, René?
So is there still an echo? Yeah. Still an echo.
yeah.
Is this now working?
One second.
If you switch off your mic, that might help. Hello. Yeah,
okay.
It's gone.
Sorry, you were talking. I think it was me. Go ahead. Sorry.
So what it actually shows, and it confirms, and it is consistent among other interpretations and also analyses, is that the AMOC is showing weakening, and this is very persistent among all the different kind of latitudes. So it's not confined to a given latitude. It's a very robust signal that the AMOC is currently weakening if you're considering a long enough time series. So that's also, of course, very good to keep in mind about climate change. Sometimes if you're taking a too short snapshot, you don't see any signals or trend is not robust. But here you nicely show that this anomaly is stronger at the beginning of the time series, and it is weakened or substantially weakening at the end of the time series.
Great, thanks. And then I would like to hear your thoughts on this. As I mentioned, this 4 watts per square meters equivalent of the Northern Hemisphere. So that's over. So the Earth has a surface of 510 million square kilometers. Half of that, if you take half of that, which is the Northern Hemisphere, and then multiply it by 4 watts per square meters, you get this 1 petawatt of heat, which is and that's equivalent to the about the doubling of CO2, which is if you translate all these other greenhouse gases to an equivalent of CO2, that's what you get. You get a doubling of already today, and that's IPCC numbers, a doubling of the greenhouse gas forcing, and this is CO2 equivalents, and here we see it in watts per square meters. So yeah, here's over the past 130,000 years to today, where you see that there's an increase relative to 7050 of a global greenhouse gas forcing of 4 watts per square meters. And maybe you can talk a bit about what does that mean for all this additional heat in the system, and when it stays, when it would stay in the southern hemisphere, but there's still this greenhouse gas forcing. Could you maybe elaborate a bit on that as far as you can, of course?
Yes, so of course it will not go down directly, but this heat transport, actually, if the AMOC shuts down, you get a different kind of heat redistribution of your system. And this actually means that we are now having like plus 4 watts per square meter of addition in the Northern Hemisphere. And we will start to see less of that. And that means that the Northern Hemisphere will not start to cool because there is still an ongoing climate change that's going on. So there is still this global warming signal pushing the temperatures higher. But it can result in below average warming compared to other places or compared to the global average. Well, on the other hand, this heat needs to be somewhere, right? Because it was first going from the southern hemisphere to the northern hemisphere, and this will translate in above average warming for the southern hemisphere. So it is actually merely a redistribution of heat rather than, oh, now our problem is solved when the AMOC collapses. No, that's not the case. It's only a redistribution issue.
Yeah, I know that's a lot of heat involved there, as we and as you highlight. It's really mind-boggling. Oh wait, yeah. So again, these numbers. I think this is a paper. It's very interesting. I don't know if you've seen it. It's drivers and distribution of global ocean heat uptake over the last half century, where you can see that a lot of the additional heat is absorbed. So heat uptake happens over the southern hemisphere, and most of that additional heat is transported northward through the Atlantic Ocean. I thought it was really quite interesting to see. So that's in a way, because of course the AMOC is still going strong and to a certain extent, right? And then part of that is stored also in these different regions. So maybe I don't know if you have any comments on this, but I thought it was just. Yeah, I thought I'll add it because it was quite interesting.
Yeah, no, I haven't read the paper, but what you already point out over here is that the Atlantic Ocean is a key player in redistributing heat across the global ocean. And of course, also for the ventilation of your deeper part of the ocean, that is also the AMOC is contributing to that. So if that comes to a shutdown, also these values will definitely change.
Great, thanks. And yeah, I think this was a. So I've really been reading your paper. So I've always also been looking at the supplements, and this is I think last year or the year before that you published this paper, and it's showing the sea ice responses to this AMOC shutdown without greenhouse gas warming. And what I really thought was interesting was what the sea ice change. So here we see the sea ice area, and here we see the global warming. But I just want to point at the changes in sea level and let me see March. So the northern hemisphere sea ice area would increase without global warming again, with this AMOC shutting down in your model, and the southern hemisphere sea ice area would decrease. Of course, because as you mentioned, there's less heat being transported from the southern hemisphere to the northern hemisphere if this AMOC shuts down. So I was thinking, would this be so the relative changes between northern hemisphere and southern hemisphere sea ice? Would that be an indicator of the AMOC strength, or could that be an indicator of AMOC strength?
Well, potentially yes, but given that there is a lot of variability both on sea ice and AMOC, and of course they're interconnected, and there are also different contributions, I think you need a very long time series to see this kind of relation showing up. So I think it is more dominated by internal variability rather than this AMOC connection. But yeah, there is, of course, what we also show in this paper, there is a link between sea ice cover, both in the northern and southern hemisphere, and AMOC strength. But I think you can't find and figure this out from observational time series which are available.
Not yet. So this is, I thought, because I saw your paper, and I just, of course, these are observations where you can see the Antarctic sea ice and the Arctic sea ice changing, and I thought,
no, yeah.
Because we have, of course, I thought maybe it could be one of the indicators available within all these other indicators to get a picture.
And. No, I can understand, but I would say, and this probably is confirmed, I'm not the sea ice expert, but this, for me personally, it shows that climate change is declining the Arctic sea ice extent and the Antarctic sea ice extent. So this is more dominated by the global warming signal rather than AMOC behavior. But probably there is some kind of AMOC signal in there, but it is much smaller compared to the interannual variability.
Yeah, of course. Yeah, so that indeed, so taking into account the global warming combined with the AMOC changes, would be quite interesting to see whether there is whether you can use this as an indicator. And then thank you again. And now my last point is so there's a different paper showing that there's a link between aerosols, especially northern hemisphere cooling aerosols like sulfur, which reflect sunlight back to space and cool the northern hemisphere, so more than they cool the southern hemisphere. And so if you have more aerosols in the northern hemisphere, that would decrease the weakening of the AMOC. And then maybe you can elaborate a bit about on whether you have looked at aerosols, or of course aerosols that we didn't emit on purpose, of course. And then also on what this study shows, again, a supplement figure of diminishing efficacy of regional marine cloud brightening in a warmer world, where they show that if you increase aerosols over the northern hemisphere mid-latitudes and the subtropics, that would increase the strength of the AMOC, or again, reduce weakening.
Yeah, I'm sorry that I also didn't, or I think I've seen the paper, but I didn't read it in detail. But the AMOC, that is driven by temperature and salinity differences. And what the aerosols actually do is that they influence mainly temperature and then also indirectly also salinity changes. So I can definitely imagine, and that's also shown in other work, is that aerosols do affect the AMOC strength. So yeah, that can in principle result in a different kind of AMOC response. And I think here you show some time series with SAI, exactly, yeah. So that,
so this is the same. So this is marine cloud brightening, and here we can see, the text is not visible here, but this is it's a preprint where they show the same, but then from stratospheric aerosol injections happening only over the northern hemisphere. So that's indeed a similar. Yeah, of course, it's a different way of cooling only one hemisphere.
But yeah, there's definitely, I think those studies and this preprint shows that there is a very strong aerosol forcing also on the AMOC, but we didn't look into detail with our studies.
And I should mention, we
thank you very much.
We interviewed Doug McMartin on that particular paper there, so people can look that up from a couple of months ago. Okay, so now, anyway, thanks, Leon. Now we're going to bring Stacy back in, and she has some questions from our YouTube community.
Yeah. Oh my gosh, so many good questions. Although one comment, Lightning Rod said, there might be some extra super computational units now that the US president has eliminated all usual clients for that compute power. So another silver lining of how he might actually be good for climate, despite being a complete, utter disaster. Will a weaker AMOC lead to less mixing of the oceans and therefore less CO2 absorption and therefore an acceleration of global warming?
Yes, I think this is a very brilliant question, that these are like the follow-up questions like a lot of people have. So what are those impacts? So I didn't look into detail, but I know my colleague, Amber Boat, so she's working on this. And she's actually showing that there can be decreased CO2 uptake, but it is not that much. But you can imagine that there is, of course, less mixing, less ventilation. So on the long run, this can definitely change this quite a lot. And she looked only until 2100 in their simulations. But there can be like these additional effects that there is, for example, less CO2 uptake when the AMOC shuts down, because less CO2 is brought into the deep ocean. So yeah, will definitely have an impact on that.
And there's a lot of chatter on, about the other water. Oh, and one you were saying with Leon, or Leon was saying something, of course, the aerosols, and it was the amount or frequency of dust moving west from Africa that affects the AMOC, I guess, as well.
Potentially, yes, but I think the AMOC will be most impacted on the northern Atlantic Ocean. So if you change their aerosol forcings, it will have a larger impact. But probably also at more of the southern latitudes, they can also probably influence that, but I'm not sure about that.
Okay. And I heard the weakening of the AMOC is and will affect flooding on the North American and on the North Atlantic coast. Is that correct in your opinion?
Yeah, so a weaker AMOC causes higher sea levels in the North Atlantic Ocean. That's also something we showed in our study from last year. And that can be up to 1 meter in some places in the North Atlantic Ocean, but we need to figure this out in much more detail along the coastline. So I don't know, I don't have the figures along the North American coastline, but it will definitely add on top of the current projections.
And is AMOC collapse considered a positive or negative feedback for climate sensitivity when considering pattern effects and the net radiative feedback parameter?
Okay, there are a lot of questions, but in the end, like an AMOC collapse is very, very bad news, and it can induce a cooling effect of minus 0.5 degrees Celsius. So that is like a very small offset of the climate, but that is still much smaller than the ongoing global warming signal we see, which is already about 1.5 degree warming. If you take, for example, 2024 as the annual average temperature anomaly. So in like giving like one shout out is like an AMOC collapse is very bad news for society. And we should avoid this at all costs.
Yes. I know. I thought a child in the background, a baby at your house, and it made me wonder, like, you know these things, and yet.
Yes, yeah. I turned a father like a month ago, so that's
congratulations.
Thank you so much. But this is also, of course, very relevant for the newest generations. Is that this may be a future scenario for them. And of course, also personally for my own child, I want to avoid such a future. And also for all my other people and my nieces and nephews. So yeah, I hope that we can avoid this potential scenario as a global society.
And it is a one-way trip. I mean, for thousands of years. Like, so once we commit to this, like, there's no going back on it. And the incredible amount of migration. It really affects the northern hemisphere the most, where most of the land is and most of the people are. So the fact that maybe you can go to New Zealand or something, there's not enough space for everyone there.
Yeah, someone was asking. They live in Finland, and it's when should I move? You know.
A good question. It depends on the future AMOC trajectory.
Yeah.
And also, it's one of those things where we're really talking about future generations. In this particular case, I mean, current climate change is going to affect us all right now. It's affecting us now. Yeah. It's going to affect our children and our grandchildren for sure. This one might be our grandchildren, whatever, but it's one way. And just imagine, 200 years ago, people saying, oh, let's screw with people 200 years from now. Let's mess up their lives by what we're doing today. And it's just not a good trade-off.
No, exactly. And that is also what I've also discussed and also mentioned in other interviews, is that any additional climate change and global warming that adds to more heat waves, to more sea level rise, to a loss of biodiversity, like all those different changes are already very severe, and that should motivate people enough to mitigate our emissions. And then on top of that, we also have these very large tipping elements in the climate system, such as the AMOC or the Greenland ice sheet or the Antarctic ice sheet, which then adds like even more disastrous climate change to that. So therefore, we should already be motivated enough as a global society to combat climate change. But currently, our emissions are still going up, and hopefully, we're hitting the emission peak maybe somewhere in this decade, so that it needs to go down as quickly as possible.
Okay, Leon, did you have another question you want to?
Yeah, just if you can bring my slide up again.
Get to that. Let's see. That's down here. That one?
Yeah, I don't want to call René out, but I think so he said there was cooling. The AMOC can cause some global cooling, if I understood him correctly, and I think that's a I think that's true. That's what some models show. But what so this paper, Earth's radiative imbalance from the last glacial maximum to present, from Bagan-Sos et al., did show that during the weak AMOC, there was a very strong increase in Earth's energy imbalance. And I think that's really, so even if there's cooling, and of course, if there's cooling, there's also less heat being radiated to space because of the Planck feedback. But also, so where does this additional heat go? Of course, also goes to melting of the ice sheets. So more melting of the West Antarctic ice sheet, for example. So I think to me, this was quite an insightful study, looking at the last glacial maximum to present, so that's from about 20,000 years ago to present, and you really see if there's signs of a weak AMOC, then there's also signs of a very strong energy imbalance. Not compared to today, because today the Earth's energy imbalance is about 1.4 watts per square meter, but for this glacial period, there was very strong energy imbalance. So I just wanted to share this with you.
Interesting.
Yeah. Okay. And I think, Stacey, are there any final YouTube questions there?
I mean, yeah, there were
a lot of them, but are any...
Yeah, it is the magnitude of atmospheric heat transport versus ocean heat transport. Does the atmosphere pick up the slack when ocean transport slows down?
Yeah, so what you actually see is that when the ocean goes down, the atmosphere tries to compensate for that quite a lot. So it can almost offset the oceanic differences, but not completely. But not completely. And therefore you see this cooling over the northern hemisphere. So there are some competing effects in the climate system trying to balance each other out, but not as effective as is. And therefore you see still this net cooling over the northern hemisphere and this net heating over the southern hemisphere.
And rather dramatic cooling over northern
wind
Europe.
is very different. Atmospheric heat transport is very different from ocean heat transport, right? Because of the very high heat capacity of the ocean. So you need very strong winds to compensate for this ocean current.
No, exactly. Yeah, so the ocean is way more effective in transporting heat compared to the atmosphere.
And
if I recall, one of the big impacts of AMOC collapse too is much stronger storms in the Atlantic than we've ever seen in human history or something. According the storms of our grandchildren, according to Jim Hansen.
Yes. So what actually an AMOC collapse does, it increases this temperature gradient, the pole gradient, and that amplifies storms.
Right. Right now it's dropping. Right now the North Pole is warming faster than the equator, so the temperature differential is dropping. It's screwing up the jet stream. We're getting all this crazy weather. But when the AMOC collapse, then southern Greenland gets way colder, like 8°C colder or something like that. And now all of a sudden the temperature differential between the equator and there is like tremendous, driving incredible storms that nothing we've ever seen before.
Yeah.
So that's just one of the many impacts. I mean, it's basically you don't want to go there is I guess the bottom line.
And also Europe, I think that was also quite interesting from your study showing that if Bergen in Norway cools like 30 degrees, right, and for example the Mediterranean doesn't, or it maybe even heats up, then you have a much bigger difference in temperature between different parts of Europe, and then that really changes the weather also, or that can change the weather of Europe in many ways.
Yeah. You will get a different circulation pattern.
Yeah. So I think this it's a good point to end on. Your recommendation is to not let an AMOC collapse occur. Is that a safe reading?
I think that's definitely a safe reading, Dan.
So on that, I'm going to thank you for being our guest again and telling us about all your latest research. And I know you're still working on some other research that's coming out soon.
Yes,
so
stay tuned.
So I hope to have you back so you can tell us about that. It's been a great discussion. I learn something every single time I speak with you, and it's an important thing. I think it's important to get the public, 90-something% of the public never heard of AMOC, but it's something that they should learn about. It's one more reason, as you said, it's not the only reason. It's just one more reason to do something about climate change as urgently as we can.
Yeah.
So thanks and good luck. Oh, and congratulations on your new baby.
Thank you so much.
May you get good sleep.
Can you already see it? Or
I was like, oh, he looks a little rougher than last time. Yeah.
So congratulations on that, and good luck with all your research.
Yeah.
Yes,
really
thank you so
appreciate
much.
your work. Thanks so much, and thanks to everyone. I always forget to say it. Please like and subscribe, and please hit the bell notification. Tell your friends. This is important climate information. The more people we can reach, the better. And so do your part.
And share this
video.
There's
Links in the description, all the papers we talked about, links to the last video, and a link to René's homepage as well. So we'll see you next time, everyone. Thanks, and bye-bye.
Bye-bye.
Bye.
I'm going to